Hello and welcome to this video on topic 6, part 1 of 2, Organic Chemistry 1. This is for EDEXCEL. My name is Chris Harris and I'm from REtutors.com, and basically this video is just going to go through an overview of the first part of topic 6, because topic 6 is such a big topic. I've decided to split it into two halves. The slides I'm using here, you can purchase them. If you just click on the link in the description box, you can get a hold of them there. They're really good value for money, and ideal for revision in terms of a supplement, the revision that you've got already, the books, the notes, etc. So it's just another way of doing it, but this time it's obviously all electronic, and you can print them off if you want. So go and have a look and go and see them there. Okay, so like I say, this is specific to EDEXCEL, and you can see that it meets these points taken from the syllabus. So in this video, we're mainly going to look at the introduction to organic chemistry. We're going to look at alkanes. We're going to look at alkenes. So we're going to look at these three parts here. The other stuff is going to be on the second half. Okay, so let's have a look at the types of formula. So we're going to look at general formula first. Basically, this is just an algebraic formula that can be applied to chemicals in the family. So for example, alkanes, alkenes, alcohols, etc. You can see here, alkanes have the general formula CnH2n plus 2. Alkenes are CnH2n, and alcohols are CnH2n plus 1 OH. Make sure you know these general formula, because then you can obviously apply them. Now obviously where it says N is obviously just the number of carbons, and hydrogen is just two lots of whatever the number of carbons is, plus 2. So that's how you basically work them out. Okay, molecular formula. Now these are the actual number of atoms in a molecule of an element. So for example, ethane is C2H6. So this is the actual number. Empirical formula is the simplest whole number of ratios in an atom in a compound. So, for example, ethane has the molecular formula C2H6. However, its empirical formula is CH3, and they do look a little bit odd because they don't look as though they actually should be chemically there. But obviously, chemically they really don't exist. But it's just showing you the whole number ratio. So if we simplify C2H6, we should get CH3. Structural formula, this is the arrangement of atoms in a molecule without showing all the bonds. So for example, butanol is CH3, CH2, 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 OH. So it's relatively straightforward. And skeletal, basically these show the bonds of the carbon skeleton only, so it looks a bit like a zigzag like this. So the hydrogen carbon atoms do not show, but functional groups are. And you can see here that this point here represents CH3. That represents CH2, that's CH2, that's CH2 as well. So obviously this is the skeletal formula for butanol. And the displayed formula basically shows the arrangement of atoms showing all the bonds and atoms in the molecule. So for example, this is 2-chloropropane. As you can see here, all the bonds, all the carbons, everything's been shown for this one. So this is the one where you show everything. So this is called the displayed formula. Okay, homologous series. This is basically just a group of compounds that have the same functional group and the same general formula. Okay, so we can use the general formula to work out the molecular formula of a compound. So alkenes have a general formula CnH2n. N is the number of carbon atoms. And the molecular formula of an alkene with 23 carbons is basically this. So we've got 23 of its CnH2n. So it's 2 times by N, which is 23. So that's going to be 46, C23H46. So that's what we use in the general formula there. Now, successive members of the same homologous group, homologous series, they basically increase by CH2 each time. So you can see here, we've got methanol. Ethanol is just in the same homologous series, but we've added an extra CH2. Propanol and butanol. And you can see here, I've highlighted in red. This is basically the formula extending by CH2 every time. Okay, and we need to know very specific homologous series. So the first one is alkanes. They end in ane. Obviously, butane is an example. CH3, CH2, CH2, CH3. So they all end in ane. Okay, so alkanes, which are branched, they always have the prefix this time. This is before it. Alkyls. So for example, methyl propane. So this is the branched bit, the methyl group, and that's the structural formula for it. Alkenes end in ene. They have a double bond. So, for example, propene, as you can see here. Alcohols end in ol. So, for example, ethanol. You can see here 2 carbons and 1 OH group. Aldehydes end in al. For example, propanol, which is CH3, CH2, CHO. Ketones end in -one, for example propanone, and these basically have the C double bond O in the middle carbon. So aldehydes have the C double bond O on the end carbon, propanones are in the middle. Carboxylic acids end in oic acid. So for example butanoic acid, CH3, CH2, CH2, COOH. That's a carboxylic acid end there, so just look out for that little bit at the end. Halogenoalkanes, or also known as heteroalkanes, fluoro, chloro, bromo, iodo, depending on obviously what the halogen is in front. Here's the example here, bromoethane, bromine attached to an ethane molecule. And cycloalkanes, so they start with cyclo, end in -ane, so for example cyclopentane, C5H10, so these are basically a functional group isomer, as you may well see, of an alkene. So you might see the resemblance there. Okay, nomenclature. Okay, so molecules are named according to rules set down by IUPAC, which is the International Union of Pure and Applied Chemistry. So this is basically the global language of chemistry, and it means we can talk about different chemicals and can be understood internationally. So the first thing we're going to do is find the length of the stem by counting the longest continuous chain of carbon atoms. So make sure you know these names here. Meth is 1, eth is 2, prop is 3, but is 4, pent is 5, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Make sure you know the stem names. That's the first thing we need to do. You can see in this molecule in particular the longest carbon chain is 4, so this means the stem is but. Okay, the functional group on the molecule normally tells you the ending of the name, so this is called a suffix. So this one has an OH group, which means the molecule will end in -ol somewhere. In fact, we've got 2 of them, but we'll come into that in a minute. Then we're going to number the carbon chain so that the functional group sits on the lowest possible number carbon. Now you can see here the lowest numbering system here is doing 1, 2, 3, 4 rather than doing 1, 2, 3, 4, because that would leave the 2 alcohol groups on the 4th carbon. So we do it the lowest possible number, so we start from 1 there. And then we make a note of the carbon, number the OH is attached to, and we place this number before the suffix. And this is an example of a butan 1-ol, because we've got an alcohol group sitting on the 1st carbon. So that is that example. Any side chains and less important functional groups are written as prefixes. So these are obviously done in alphabetical order. So you can see here that we've got a side chain in this example. This is a methyl group hanging off the 3rd carbon. So we need to do this in alphabetical. And if there is more than one identical functional group, then we put the prefixes di for 2, tri for 3, or tetra for 4. Okay, so let's have a look. This one is called 3-methyl butan 1,1-diol. Because we've got 2 alcohols, we put di in front of it, so it's diol. And 1,1 tells us that both of them alcohol groups are sitting on the 1st carbon. The 3 bit tells us the where the methyl is coming from. You can see here there's the methyl group that's sitting off the 3rd carbon. So this one is 3-methyl butan 1,1-diol. Okay, so classifying reactions. So make sure you know what type of reaction we're dealing with. This is quite important. So polymerization is basically where you're joining smaller monomers together and they form these really long chains. We've also got elimination. Basically, these are some atoms that break away from a larger molecule. You'll see examples of these all the way through topic 6. So you do need to know what these are. Hydrolysis is basically the splitting of a molecule into 2 using OH- or H+. This comes from a water molecule. So again, hydro meaning water, so you might be able to get it from there, and lysis meaning to break or to split something, so it's hydrolysis. And addition reactions, these are basically just joining molecules to form larger ones. That's pretty straightforward. Substitution reactions, these are replacing one atom with another on a molecule, so we're just swapping like for like. You'll see some of them later on, like I say in topic 6. Reduction reactions, this is when something gains electrons. Remember your oil rig acronym, reduction is the gain of electrons, so that is classed as reduction. And obviously oxidation is the loss of electrons. Remember that oil rig acronym again, so it's oil, which is oxidation, is loss. Okay, mechanisms, so you're going to see quite a few of these in topic 6. So chemical mechanisms, they show the movement of electrons during a chemical reaction. And we use curly arrows to show this movement of electron pairs. And they always start from an area with an area of electrons, high area of electrons, for example, a double bond or a lone pair of electrons, and it goes to somewhere with not many electrons, in other words, an electron deficiency. So this is the curly arrow here. And basically the arrow can represent either the formation of a new bond, or it could actually show the breaking of a bond as well. So if the electrons are moving from a bond onto an atom, then obviously you're breaking a bond. You'll see free radical mechanisms as well, but we don't need to know any curly arrows for them, which is pretty useful. So yes, okay. So a mechanism showing how OH minus ions reacts with bromoethane. Right, this is just going to show a generic example of how a mechanism works. You can see here, here's our bromoethane. You can see we've got one bromo with 2 carbons here. We've got an OH minus ion here with 2 lone pairs. We're going to show basically how we can demonstrate this as a mechanism. So remember, electrons move from an area where there's loads of electrons. In this case, the electrons are on the lone pair to a delta positive carbon, because this has an area of electron deficiency. And because this is effectively trying to form a bond, basically we need to break a bond, otherwise this carbon's going to have too many bonds. It's going to have 5 instead of 4. So the electrons from this bond are then going to break and jump onto the bromine. This is going to effectively break off and form a Br minus ion. Okay, and here's just our product here that we've produced. Now the OH minus obviously would have come from sodium hydroxide, this bit here. So anything with hydroxide in really would have brought about that. And the Na plus in sodium hydroxide, that doesn't get involved, so we don't include it in the reaction. It's called a spectator ion. But you can see this example here is substitution, because we've swapped the bromine for our OH. So this is an example, a bit like the different types of reactions we've seen before. Okay. So, types of mechanisms. We looked at different types of reactions, as we've seen before. That's like addition, reduction, elimination. And, sorry, that's my phone. And we're going to be looking at, obviously, types of mechanisms as well. So, here are the mechanisms. We've got free radical or radical substitution. Basically, this is used in reacting halogens to alkanes. Remember, alkanes are pretty unreactive, so we need to use really reactive radicals to actually get that going. Electrophilic addition, this is basically used in adding halogens and hydrogen halides to make alkenes. Used for adding halogens and hydrogen halides to alkenes. So alkenes obviously got loads of double bonds. And we make halogenoalkanes, so we're adding to that double bond in the alkene to form the halogenoalkane. And the other type is nucleophilic substitution, as we've just seen as an example before. This is used in primary halogenoalkanes and aqueous potassium hydroxide. This is used to make alcohols. And so amines are made by reacting ammonia with halogenoalkanes, or you can use acid chlorides as well, if you wanted to. So there's a few different varieties there. Anyway, you'll see a few more examples later on. Okay, so structural isomers. We need to know 3 different types of structural isomers. Okay, we need to know chain, positional, and functional group. Now, structural isomers, basically they have the same molecular formula, but they have a different structural formula. And like I say, we've got 3 types. So we're going to look at chain first. Now, this basically is the same molecular formula, but different arrangement of the carbon skeleton. So for example, pentane, and it can be rearranged to form 2-methyl-butane. And you can see here, this is an example of a chain isomer, because we've changed the carbon skeleton, as you can see on there. Okay, positional isomers, these have the same molecular formula, just like before, but they have a different position of the functional group on the carbon skeleton. So you can see here, here's pentan 1-ol, the alcohol group is sitting on the first carbon, and pentan 2-ol is basically the alcohol group is now sitting on the second carbon. So this is a positional isomer. So these two are positional isomers of each other. And finally, the last one is functional group isomers. These basically have the same molecular formula, just like the start of before. So notice the starts are all the same, but we have different functional groups. So here's the example. This is pent-1-ene. You can see we've got an alkene group here. There it is there. There's the alkene group. And the functional group isomer is cyclopentane, like we mentioned before. This is obviously just 5 carbons. All we've done is looped these carbons together to form a cycloalkane. Okay, so these are functional group isomers. No double bond in there, that's why it's a functional group isomer. Okay, and you've got to be careful with isomers because you've got to make sure that you've actually drawn a different molecule and not drawn the same one but just drawn it in a different shape. So you've got to make sure you've drawn it differently. So the key point really to avoid this is find that longest continuous chain. Okay, so it doesn't matter what the shape is, the longest continuous chain takes priority and is vital that you find it. So let's have a look at this one. For example, this is pentane. Obviously it's 5 carbons in a row, but this one is still pentane. Even though we might have drawn it in like a zigzag shape, it's still pentane. So make sure that when you draw these, you actually have drawn something which is different from what you had before. And finding that longest continuous chain will help you to decide if it is actually an isomer you've drawn or just the same molecule, just drawn differently. Okay, so let's have a look at some alkanes. Now, alkanes are saturated hydrocarbons. They have the general formula CnH2n plus 2. Okay, alkanes are hydrocarbons, which means they contain hydrogen and carbon only. They're saturated. Each carbon's bonded 4 times with the maximum number of hydrogens possible. And you can see here there's methane, ethane, propane. These are all examples of alkanes. Cycloalkanes are slightly different. We've seen them just before. They have the general formula CnH2n. They've got 2 hydrogens per carbon. So an example here is cyclopentane. And cycloalkanes, they're still classed as saturated, though we still do have a maximum of hydrogens per carbon. So these are still classed as saturated. But obviously their general formula is obviously different from a standard alkane. Okay, bond fission. So there's 2 types of bond fission occur, we should say. Homolytic and heterolytic fission. So bond fission is basically just the breaking of a covalent bond. Okay, and the electron pair in the bond can be distributed in 2 ways. So we're going to look at heterolytic first. This is basically where we get a bond that's breaking, but the electrons are distributed unequally from 2 different ions. So we've got a cation and an anion. So we use a double-headed arrow. In this case, you can see here, to show the movement of a pair of electrons, and hetero meaning different. So you can see here that we've got both electrons moving to one atom, so we get this Y minus here and X plus. So we get two ions being formed, a cation and an anion. Okay, and homolytic fission, this is basically where we've got, again, we've still got a lone pair in the middle of the bond, except one electron is going to go one way and one electron is going to go the other way. So we have this homolytic, homo meaning same. So we're forming the same type of product. We form an X dot here and a Y dot. So both of these are radicals, and obviously these radicals are pretty reactive. So we need to obviously know that we've got 2 ways in which we can form them. Heterolytic fission, which is basically both electrons going to one atom forming 2 different ions, and homolytic fission, 1 electron going to each atom forming 2 radicals. Okay, so let's have a look at some free radical chain reactions. So chain reactions involve 3 main stages. We've got initiation, propagation and termination. So initiation steps, these are basically radicals are produced because it's initiate. If you initiate something, it means you start something happening. They're basically produced from UV light. We call this a photochemical reaction because we're using light. The bond breaks producing 2 radicals. Propagation is basically where we've got a radical reacting with a non-radical, and new radicals are created, and they then go on to react with other non-radicals, and this is why we call it a chain reaction. As you'll see later on, you'll see an example. And termination is basically where we get 2 radicals reacting together. They form a non-radical molecule, ends the chain reaction, and this is why it's called termination, because we're ending the reaction. Okay, so chloromethane can be made via this reaction in particular. You can see here that we've got this reaction here. So sunlight breaks the CL-Cl bond, in something called photodissociation, so meaning breaking up the bond using light. Okay, so the bond breaks equally, so it's a homolytic fission, and it's producing 2 really reactive halogens, and there it is there, Cl2 with a bit of UV light producing 2 lots of Cl dot. Okay, propagation, so this is where the chlorine radical from what we produced before reacts with methane molecule to make a methyl radical, and then that methyl radical reacts with another unreacted chlorine molecule forming chloromethane, as you'll see in a minute, and then that Cl radical then reacts with more methane, and that is obviously what makes it a chain reaction. So we've got two stages to propagation here. We've got the first stage here, which is chlorine radical reacting with your methane, which is this bit here, and it's a little bit like past the radical. So you're forming your CH3 dot here and HCl. Okay, so this is an example of a radical being formed from essentially being formed from a radical and a non-radical. So you can see here, all we've done is the hydrogen that was on here is now part of HCl, and the radical is now on here. Now the radical here then goes on to react in the second step, which is this one here. So that reacts with more chlorine, this is the unreacted chlorine, to form your chloromethane and chlorine radical. And this chlorine radical, remember, the product of the second step must be a reactant in the first step. Okay, so them two must react together. Okay, so very important. And the final stage is obviously termination. So you can see here that's supposed to say chloromethane, my mistake. So two radicals react to make a stable non-radical molecule. So for example, forming chloroethane. Okay, and this chloromethane, because that's obviously what we're making. So here it is here. So we've got the CH3 dot and the Cl dot. These obviously react together to form chloromethane, which is this molecule here. I mean, you could do it with bromomethane. Obviously, there's no different. Instead, this would be Br2, but it's the same mechanism. So yeah, but obviously in this example, you can see it's forming chloromethane. Okay, so products of free radical reactions. So producing just chloromethane is actually pretty difficult. Loads of reactions occur, and we actually produce a mixture of different products. So if there's loads of chlorine, okay, in other words, we've got it in excess, then we get di, tri, and tetrahaloalkanes. So you can see here, there's our chlorine radical reacting with our chloromethane that we just made. That can react further, obviously, and we can form this radical in HCl, and then this radical product here comes down to the second step, reacts with unreacted chlorine, as we can see here, and that produces dichloromethane and Cl dot. And then obviously that dichloromethane can react further to form trichloromethane, as you can see here. There it is. And trichloromethane can react further to make tetrachloromethane. So it just keeps on reacting. So we get loads of different products with this. So we have to separate these. If we want one product, say if we were only in the business to make chloromethane, and this reaction wouldn't be particularly that good using this current setup with loads of chlorine in there, because we actually form loads of impurities. We form dichloro and trichloro, etc. So we all have to separate them. But there is a kind of a solution. If we add excess methane, this will reduce the amount of multiple substitutions that we get, and we get a greater chance of chlorine reacting with methane. So in addition to multiple substitution, we can also get isomers formed as well. And this is because the free radical substitution can occur anywhere on that hydrocarbon. So we can get one chlorobutane, for example, or two chlorobutane. So we can even get positional isomerism. Remember, that's changing the position of the functional group on the alkane chain. So actually, one way of getting around this is obviously adding your excess methane instead of chlorine. So as long as you got more of that, then that's going to be more important. But obviously, that doesn't get around this idea of different isomers. So it is quite difficult to react. Although, as useful as they are in terms of really reactive, you don't use much energy, they are a bit of a pain because you don't get a pure product. Okay, so fractional distillation. So alkanes are found in crude oil. Obviously, that's a mixture of different length hydrocarbons. So you can see here that we've got, obviously, our fractionating column here. And crude oil is basically vaporized using a furnace to about 350 degrees Celsius. And you see, it goes into here. And the vaporized oil enters the column, so here it is here, goes in here, and rises through the trays. The longest hydrocarbons don't vaporize, and so they condense down to the bottom. So these ones will form a slurry down at the bottom here. So if it's really long hydrocarbons, your smaller ones will start to rise up through the column. Right, now, the column has a temperature gradient, okay? It's cooler at the top over here, you can see 20 degrees up there. And obviously, as the vapor rises, different parts of that mixture will condense at different temperatures. So we've got our shorter hydrocarbons condense further up at the top there. These are the ones with a shorter chain length. And your longer chain lengths, because they've got more van der Waals forces, or sorry, London forces, sorry, because they've got more London forces, they have they obviously have higher boiling points, and so they will just form as a solid or a slurry down at the bottom there. And the idea with the fractionating column is that we can separate these fractions obviously according to their boiling points, and we get different fractions. So at the top here we get 1 to 4 carbons. Around here, gasoline or petrol, 5 to 12. Kerosene is about 11 to 15. Diesel oil is 15 to 19. Fuel oil is about 20 to 40. And anything more than 40, you're starting to get into solids here. So these are just rough guidelines. They're not precisely correct. Okay, so these shortest hydrocarbons, these ones here, like I say, these won't even condense at all. They'll still stay as a gas even at room temperature. And obviously these ones come off at the top. So these are like your butanes, your methanes, your ethanes, etc. Okay, so these fractions can be used for loads of different things. So for example, your gases at the top can be used in LPG or stove gas, liquefied petroleum gas, that's what LPG stands for, used in some cars. Petrol, obviously used in petrol cars. Kerosene is used in jet fuel. Diesel oil is used as a bit heavier oil. This is used in trains. Fuel oil is used in ships. It's even heavier, much really calorific, loads of carbons in there, but obviously quite polluting as well. And bitumen is used in roofing and tarmac. So this is the slurry that you'd get at the bottom. Okay, so heavier fractions. Sometimes when we do this fractionating column, when we fractionate them, we get it's kind of potluck about the amount of each fraction that we get. And some fractions aren't in big demand as some others, and heavier fractions can be cracked to higher demand lighter fractions. So we're talking about fractions which have got really long hydrocarbon chains that are not in as big demand as your shorter ones like gas, natural gas, and petrol. So fractional distillation, like I say, produces a variety of fractions, but the demand varies. Heavier fractions, like I say, like fuel oil, are in lower demand than lighter fractions such as petrol, which are a lot more valuable. So what we can do is we can take the heavier fractions, crack them, and basically this allows us to break your longer hydrocarbon chains into shorter ones. So an example would be dodecane, which is C12H26, forms ethene and decane. And you can see here that we've cracked it. We've taken the longer hydrocarbon and broken it down into two smaller molecules. So there's two types of cracking we need to know about. We've got thermal cracking and we've got catalytic cracking. Okay, so thermal cracking. Basically this happens at a high temperature and pressure, and we're using about 1,000 degrees Celsius, and 70 atmospheres of pressure. The products of thermal cracking are mainly alkenes, which is really good for things like plastics. Like I say, so we can use polymers, and for example, propene is used to make polypropene, so we're made of plastic from it. Catalytic cracking, though, is slightly different. High temperature and slight pressure is used, so 450 degrees Celsius. Zeolite catalyst is used, helps to lower that temperature, means we don't need as much heat energy to obviously get this reaction going. Products of catalytic cracking are mainly aromatic hydrocarbons. These are useful for petrol and diesel. So basically aromatics are just things, molecules which have benzene rings in. It's got 6 carbons with a delocalized electron system, but don't worry too much about aromatics, but you do need to know that catalytic cracking does mainly produce your aromatics. And obviously using that zeolite catalyst, it lowers the temperature and pressure needed for cracking to occur. So obviously cracking via catalytic cracking has a lower cost and also speeds up that process. As they say, time is money. Okay, we can reform alkanes as well. So basically these are reformed into cycloalkanes and aromatic molecules. This is quite an interesting bit of chemistry. So obviously we know about cracking, where we're taking long hydrocarbons and 2 shorter ones. This is called reforming. So petrol and diesel are made from a mixture of hydrocarbons, some of which are straight chain hydrocarbons. Okay, so quite a few of them are. But the problem is that these straight chain alkanes create knocking in a car engine. Okay, and this is where straight chain alkanes explode upon compression. So in an engine we have pistons, and the pistons compress the fuel and obviously ignite it at the same time, and the energy from the ignition pushes the piston down, and that drives the wheels forward. So, but we do get this knocking. Basically, in adding branched and cyclic alkanes reduces this knock-in and actually increases the engine efficiency. So cyclic and branched alkanes, these can be made using straight chain alkanes and a platinum catalyst, and this process is called reforming. So we're taking the same alkane and just reforming it into a cyclic or aromatic compound. So you can see here in this example, or branched one, should we say, as well. So you've got 3 different alternatives. But you can see here we've got octane, which is 8 carbons. We're adding the platinum catalyst there, and we're getting this branched alkane, which is the more of this we have, or higher amounts of this, should I say, in the petrol, this reduces obviously knocking in the engine. You see here this is obviously branched. It's an isomer. Or we can take hexane is reformed to cyclohexane and then to benzene. So you can see here we've got hexane, which is 6 carbons. Add a bit of platinum and we get cyclohexane, and then if we add platinum again we can form benzene. So these have the similar effect as branched alkanes as well. Okay, so complete combustion of alkanes. So alkanes burn in oxygen completely. Okay, so we've got a plentiful supply of oxygen, and they form carbon dioxide and water. Now they're good fuels. They most will burn readily, and they'll produce loads of energy, which is great. And basically, the longer the hydrocarbon or the alkane, the more energy they produce. So they're used to power vehicles. Most of Britain's electricity is actually made using hydrocarbons. So we've got gas power stations, and we've got coal as well. Obviously, well, coal's not really a hydrocarbon, but it's still a fossil fuel. So we do produce a lot of electricity using fossil fuels. Okay, and basically we're just burning these alkanes. So the complete combustion of butane. Here's butane here. This is natural gas. Remember, reacting with oxygen form carbon dioxide and water. Just make sure you're able to balance these equations as well. All combustion reactions involve the reaction with oxygen forming carbon dioxide and water. Obviously, in the real world, we don't get complete combustion all the time. We do get incomplete as well. And this is basically when alkanes burn with a limited oxygen supply and we produce carbon monoxide and soot. And this is obviously incomplete combustion is occurring. So here's an example of incomplete combustion of butane. And you can see here that we're producing carbon monoxide and or carbon dioxide. Here's an example here. This is butane reacting with oxygen to form carbon monoxide and water. This is just an example showing how it can react with carbon dioxide, so it can produce both of them. In reality, this is what happens in the second equation. Now, carbon monoxide is poisonous. What it does is it binds to hemoglobin in your red blood cells, and it prevents the oxygen from binding to it. So, effectively, it's suffocating you. And carbon monoxide, luckily, can be removed using catalytic converters in the exhaust system, and obviously this reduces the toxic emissions. So the incomplete combustion for butane producing soot, just as an example, soot is just carbon, pure carbon, so we're just balancing it there. There's our butane, and we're producing this black soot. This is more likely to occur with longer hydrocarbon chains. And soot basically causes breathing problems. It makes engines dirty. It does, it clogs up the engines, and it makes buildings dirty as well. That's why obviously it keeps the window cleaners in business, I suppose. Yeah, it's obviously it's not great, but the most thing is that it exacerbates asthma, so people breathe this stuff and it isn't very good. Okay, acid rain. Burning fossil fuels can release sulfur dioxide and oxides of nitrogen. These contribute to acid rain. So acid rain basically causes damages to plants and fish, and causes erosion of buildings. So some fossil fuels, they contain sulfur-based impurities. So coal, for example, contains loads of sulfur. Obviously, when we burn this, that sulfur then reacts with the oxygen in the air to form sulfur dioxide. And this sulfur dioxide is an acidic gas. So when it goes into the atmosphere, reacts with the moisture in the water, moisture in the air, and then it forms as acid rain. So forming sulfuric acid. Nitrogen oxides or oxides of nitrogen do the same as well. Basically, with oxides of nitrogen, these are produced when nitrogen and oxygen is heated. So we've got nitrogen naturally in the air and oxygen. And when we've got a high enough temperature and pressure, we form oxides of nitrogen. And again, these react with the moisture in the air to form nitrous oxide. Or nitric acid, sorry. Okay, so this obviously dissolves in the water, and this obviously forms as acid rain. Okay, so not very good so far with these fuels. Okay, catalytic converters. So like I said before, we've got this bit of a solution really. We're using catalytic converters in vehicles to help reduce some of these harmful pollutants that go into the atmosphere. So catalytic converters have basically reduced the amount of unburnt hydrocarbons and oxides of nitrogen going into the atmosphere, which is great. Catalytic converters normally contain platinum, rhodium and iridium metals. So some very, very expensive, exclusive metals that's put into these exhausts. And basically what they do is they convert harmful gases like carbon monoxide, oxides of nitrogen and unburnt hydrocarbons, and they turn them into less harmful products like water vapour, nitrogen and carbon dioxide. Now here, nitrogen monoxide is being converted, and you can see here there's nitrogen monoxide, to nitrogen and oxygen. Now these are far safer to emit than nitrogen monoxide. So the catalytic converter is actually doing that, which is pretty useful. Okay, so fossil fuels that have been created, or fossil fuels, sorry, are actually created from dead animals and plants lived millions of years ago. So there's a lot of heritage to these things, and we've used them for, well, mainly very recently we've used more than ever the fossil fuels, but they obviously are non-renewable. Now, they are non-renewable. They're made up of mainly coal, oil and gas. So obviously the coal we can dig up from under the ground. Oil can be dug up under the ground as well, and so can gas, but coal normally find on coal seams, so you can dig that up mainly from land. Oil and gas we can go off abroad, offshore, so we can go and dig it up from the sea. Okay, so coal, oil and gas can be extracted easily. They're pretty good sources of energy as a fuel, so that's pretty useful. But on the other hand, fossil fuels will run out. Oil in particular is in a really, really short supply. We don't have a lot of it left. It's becoming increasingly more difficult to extract, and with that difficulty means the cost of extraction is going up as well. And so that's obviously going to be a bit of a concern, as quite a few economies are obviously based heavily on fossil fuels and the use of fossil fuels, and obviously if they go up, everything that relies on fossil fuels will increase as well. So that could be food prices, etc. Okay, biofuels. So we use bioethanol, biodiesel and biogas. All these are renewable sources of energy, so as an alternative to fossil fuels. Basically, ethanol is being used as a fuel in countries where there's a good supply of sugarcane. So, for example, Brazil is one of the countries where they're using bioethanol. This is added to petrol as well, so it reduces the complete reliance on fossil fuels. Now, biodiesel is obviously this is obviously a type of bioethanol. This one here, but biodiesel is made from refining oils and fats, so we can recycle some of these, like chip fat or chip fat oil, etc. And biogas is made from the breakdown of organic matter, and you'll see a few of these as well. So basically, the sugar, like you can see here, is harvested and it's fermented, and we produce the alcohol from that. Now, the advantage of using this is that biofuels are renewable, so they are more sustainable than crude oil, and they produce carbon dioxide when they're burned, but they're classed as carbon neutral because some of the carbon dioxide is absorbed by the plants when they are growing. And the disadvantages: they are expensive to convert existing petrol engines to take fuels with higher concentrations of ethanol, and the land that would have been used to grow food is now actually being used to make fuel instead. And in countries where there's a food shortage, that can be a little bit of a concern, because it's only going to make the cost of food increase even more, obviously because of the shortage of food, despite an increase in the population. So, for example, India and Brazil are the main countries which grow sugarcane. Okay, so let's have a look at some alkenes. Alkenes are unsaturated hydrocarbons. They have the general formula CnH2n. Now, obviously, this formula only applies if you only have one double bond in there. So alkenes, these are hydrocarbons, which means they contain hydrogen and carbon only. They're unsaturated, means that there's at least one double bond in there, double covalent bond, and they undergo addition reactions, as you'll see in a minute. So here's some examples here. This is ethene, CH2CH2. And this is butyl-1,3-diene, which is this one here. Now, I've got the di there because we've got two of them. Ene, obviously, because it's an alkene. And 1 and 3 because we've got the first and third carbon. Remember, we've got to number them in terms of the lowest numbering system. The double bonds have a really high electron density there, which makes them pretty useful for reactions. So they're pretty reactive, especially compared to alkanes. And cycloalkenes, these have 2 fewer hydrogens than their straight chain counterparts. And you can see here there's a cyclopentene, which is C5H8. Okay, sigma and pi bonds. So double bonds contain sigma, which is this little symbol here, and pi bonds, which is this symbol here. Now, sigma bonds, these are basically when you've got two s orbitals that are overlapping. They align horizontally and they give this single covalent bond. Now, what we have is a strong electrostatic attraction between the nuclei and the shared pair of electrons due to this high electron density between the nuclei. So we've got this loads of electrons here, obviously where they're overlapping. Now, what this does, this makes the sigma bond have a really high bond enthalpy. And it is the strongest type of covalent bond as well. Pi bonds, on the other hand, this is where we've got p orbitals that overlap, and these obviously overlap parallel to each other. You can see the two pi bonds there. And p orbitals, these are dumbbell shaped, and when they merge, they form two oblong shapes, one on top of the other, and obviously you have your nuclei in the middle here, and you can see that they've obviously merged together to form obviously these bonds here. Now, pi bonds are weaker than sigma bonds. Their electron density is spread out a little bit more, and obviously the electrostatic attraction is weaker. So pi bonds obviously have a lower bond enthalpy. So in terms of breaking bonds, breaking a pi bond is going to be easier than breaking a sigma bond, and you'll see that quite a lot in these reactions. Okay, so the double bond has a high electron density, like I say. So alkenes, they have the sigma and pi bond, and this high electron density area makes them really reactive. So you've got 4 electrons are being shared in that double bond, remember. Okay, alkanes only have sigma bonds, so obviously the CH and the CC bond has obviously just got a single bond between them. They're non-polar as well, so they're not very reactive compared to alkenes. In fact, they're pretty boring. The only way really you can get them to react is using a radical. Now, you can see these pi bonds, they stick out a little bit, and the whole double bond has a high electron density. As you can see there, loads of electrons mixed in there. This means they're open from attack from electrophiles. These are electron-loving species. They normally have a positive charge, and so therefore they have an electron deficiency. And this is a little bit like a hot dog, actually. It's a bit of a my sense of humour coming through there, which is which is true. I mean, you can see obviously you've got the sigma bit in the middle and the pi bond either side. If it helps you to remember the what this thing might look like, then it might help. So the pi bond has a low bond enthalpy too, which means it gives a reason why alkenes are so reactive. So you need to know obviously these reasons as well, and there's a few reasons there. They're good starting products for polymers. You'll see in a minute they're used for polymers quite a lot, and petrochemicals as well. So alkenes are incredibly valuable. Okay, stereoisomers. They have the same structure formula but a different arrangement of atoms in space. So for example, EZ isomerism is the one you're going to see quite a bit. Now this CC double bond, it's basically all of the bonds that are bonded directly to the carbon in a CC bond are all flat, they're planar. Okay, and you can see here in this diagram. So the shape of it is actually trigonal planar. It has a bond angle of 120 at the end here, so watch out for that. The atoms, they can't rotate around this double bond as well. It's rigid, it's fixed. Now this obviously gives it rise to this EZ isomerism, or we call it stereoisomerism. And that's quite unique to alkenes. So you can see here, these two are stereoisomers of each other, and they have the same structural formula, CH3, CH2, CH, CH3, but we can't twist that double bond. And you can see here that we've got different isomers. So you can see here we've got the 2 hydrogens here on the bottom, and here the 2 hydrogens are opposite each other. So you can see these are isomers. Remember that double bond can't rotate, so these can't rotate round to form the same structure as that. So they are called stereoisomers. So you can see here these 2 isomers have restricted rotation around the double bond, as we've said. And you get the EZ isomerism, where you have 2 different atoms or groups of atoms on the same carbon. You can see here we do have 2 atoms on the same carbon, 2 different groups of atoms on the same carbon, and the same here. So this one does have the potential of EZ isomerism. And we can name these molecules either E or Z. So E meaning entgegen, which means opposite, and basically the same groups are opposite the double bond. So this would be an E version because the same atoms are opposite the double bond. And Z means zusammen, which means together. This means the same groups are on the same side of the double bond. So you can see here, the two hydrogens are the same side of this double bond. So obviously that one's called Z-pentuene because it has got the two atoms on the same side. And this is E-pentuene because the hydrogens are on the opposite side of the double bond. Okay, so these can also be called cis, which means the same side, or trans, which means on the opposite side. Okay, we need to know something called about the Cahn-Ingold-Prelog rules. Okay, a bit of a mouthful, but we do need to know about them. So we're going to use these KIP rules, or Cahn-Ingold-Prelog rules, when deciding if an isomer is E or Z when we have 4 different groups around a double bond. Okay, so in the other examples we had 2 hydrogens, so it was a little bit easier to spot. A little bit tricky with this one. So what we have to do is first label all the carbons with the double bond as carbon 1 and carbon 2. And then the second thing, we need to calculate the atomic number, not the mass number. Okay, it's the atomic number of the first element directly bonded to the CC double bond. And the atom with the highest atomic number is given a higher priority. So you can see here, the first atom here is carbon. That's got an atomic number of 6. Bromine's got an atomic number of 35. That's bigger, so that's taken high priority. And on the other side, you can see here again, carbon 6, hydrogen's 1. That's taken the higher priority. So we've got the 2 high priorities opposite the double bond here. So because we have them opposite of the double bond, we call this E2 bromopent2ene. Okay, so we've got 2 high priority groups opposite the double bond, so we call it E for Entgegen. You may have to check further down the chain though to work out priorities, so let's have a look. So again, you can see here on carbon 2, we've got 2 carbons immediately bonded to carbon 2. So you can see we've got a carbon there and a carbon there. So both of these have an atomic number of 6. Now this is going to be a problem. What we have to do is check further down the line. So let's have a look. So if we look at the next atom down on the chain, there's another carbon on the ethyl group. There it is there. Okay. And this has an atomic number of 6, but just a hydrogen on the methyl group, which is obviously this one here, which is carbon number 1. So let's look at our priorities again. Hydrogen is an atomic number of 1, bromine is an atomic number of 35. That's higher, so that takes the higher priority. And on this side, the atomic number is 6, then 6. So that takes a higher priority, whereas this one is 6, then 1. So this one takes the higher priority. Again, this one takes the higher priority, and they're opposite the double bond, so we call this E1 bromo 2 methyl but 1ene. Okay, so this is an E1 because they're opposite the double bond. Okay, electrophilic addition. So alkenes are attacked by electrophiles because they've got this double bond. Okay, so double bond has high density of electrons and is attacked by electrophiles, and the electrophile adds to the molecule. So an electrophile is an electron pair acceptor, and they are deficient in electrons and are attracted to the double bond. So examples of electrophiles are things with a positive charge like NO2 plus and H plus. Here's some more examples. You might get delta positives as well. So HBr, for example, obviously the hydrogen's got the delta positive on there, and H2SO4, again the hydrogen holds the delta positive on that example. So all electrophilic addition reactions, the curly arrow starts from the double bond, and this is a generic example showing it. We've got the E plus there to represent an electrophile, and this is obviously accepting electrons from the double bond. And another example, which is quite common as well, is the addition of hydrogen to a double bond, and this is basically using ethene, which is just 2 carbons at 150 degrees Celsius and a nickel catalyst. What this does is it makes ethane. So there's the ethene there, plus hydrogen, that forms ethane. So you can see this is the addition of hydrogen onto a double bond. Okay, so the addition of bromine is also a test for alkenes as well, but you need to know the mechanism for it. So we've got a test for alkenes is the decoloration of bromine water. So adding bromine water to an alkene causes a colour change from brown orange to colourless. Now, bromine is the browny orange chemical, and this is the electrophile, and this is adding to the alkene, forming a dibromoalkane, and it's the dibromoalkane that's actually colourless. So you can see here, there we've got our bromine. Now, bromine is normally non-polar, because both bromines are electronegative as each other. However, when this bromine molecule comes close to an alkene, or an area of high electron density, the electrons in the bromine move from one side of the molecule to the other because they're repelling each other. And we get this temporary dipole being created. And it's this little mechanism here that basically allows it to add onto this double bond. So you can see here we've got the electron pair in the double bond is attracted to the now delta positive bromine and forms the bond. And this also breaks the Br-Br bond. So let's have a look. There it is there. So the electron's going from the double bond onto the Br delta plus, sorry. And then obviously that bond breaks and the electrons move onto the bromine on the other side of the molecule. So what we form is this carbocation intermediate. This is formed. You've got your Br minus as well, which we had formed over here. And this is obviously attracted to your positive carbon atom in the molecule on the carbocation. Now the electrons on here, they go onto this not delta positive, proper positive or carbocation here, and obviously this forms your colourless 1,2-dibromoethane, as you can see here. Okay, hydration of alkenes. So alcohols can be produced or prepared by the hydration of alkenes. So what we can do is we can use steam and an acid catalyst or H+, to create an alcohol. And we can make ethanol by reacting steam and ethene with a phosphoric acid catalyst. And we've got a temperature of 300 degrees Celsius and a pressure of 60 atmospheres is also needed. Okay, so you have to remember them conditions. So here we've got the reaction here. So we've got ethene reacting with steam, which is obviously just water, and we form our ethanol here. So make sure you're able to obviously write the reaction down for this. Now this is a reversible reaction, but initially the yield's actually only 5%, which is pretty poor. But thankfully any unreacted alkene is recycled, and the overall yield for this reaction is actually a much more respectable 90 to 95% for this reaction. So it's pretty useful for making ethanol using an alkene. Okay, so we're forming alcohols from alkenes. So alcohols can also be made from alkenes using acidified potassium manganate. Okay, so if we add purple, which is your potassium manganate, not manganite, that should be manganate, sorry, that's a mistake. Okay, so acidified potassium manganate solution to an alkene, and this will lead to the solution turning colourless. I think that's my auto spell on. So obviously got slipped through the net, that one. So potassium manganate, there it is again, look. Potassium manganate, okay, which is this here, is an oxidizing agent and oxidizes the alkene to make a diol, which is your two OH groups. Okay, you're looking here. So let's have a look. Here it is here. There's your manganate ion here, MnO4- and your H+. So there's your ethene. Using your acidified permanganate solution, and you'll form your diol, ethane 1,2-diol. You can see here, there's the double bond, and there's the two alcohols that are being added. So all we're doing is we're basically adding this purple potassium manganate solution. Remember that's an 8, not an 8. Okay, that's not the case, so that just needs to be changed. There's manganate with an A. Okay, and obviously that's reacting to form our diol. Okay, addition of hydrogen halides. So alkenes, like I said, they react with quite a few things here. So we've seen the addition of hydrogen, we've seen the addition of bromine, we've also seen the hydration of them as well, so adding water with steam. This one we're going to add a hydrogen halide and we're going to form a halogenoalkane. So for example, HBr follows the same mechanism as the addition of a halogen, so it's exactly the same. So the mechanism can apply to other hydrogen halides and alkenes as well. So here it is, look, HBr this time is fully polarized as a permanent dipole. We have the alkene here. And again, the electron pair in that double bond, we've got loads of electrons in there, is attracted to the delta positive hydrogen on the HBr, and this obviously breaks that bond. So there it is there, the electrons come from the double bond onto the hydrogen, that forms the delta positive, and then that breaks to form the, obviously the electrons move on to the Br minus, so the delta minus on the bromine. A carbocation intermediate is formed, which you can see there, and the Br minus is attracted to the carbon plus. This is your carbocation, there it is there. Okay, and so what you form is bromoethane. Obviously the hydrogen's been added here, and obviously the bromine's then added at the end. So it is actually the same mechanism as the one for bromine. Okay, so reacting hydrogen halides with unsymmetrical alkenes, though, what we do is we produce two different products, and this can be I'm going to be really careful with this as well. So the amount of the two products is determined by the stability of the carbocation intermediate that we'd seen just before. And basically, the more alkyl groups bonded to the carbocation, the more stable that intermediate is. So this is because the alkyl groups, what they do is they push electrons in to that positive carbocation, it stabilizes it. And so the more stable that carbocation is, the more likely it will form. And obviously the products that are formed from that carbocation is obviously going to more likely to form them as well. So let's have a look at this one. So there's a primary carbocation. The R just represents an alkyl group, and the red arrow just shows which way the electrons are being donated. So this R group is pushing electrons into this carbocation. This is called a primary carbocation. Obviously your secondaries are more stable and your tertiaries are more stable again. Again, we've got two R groups here pushing electrons into this carbocation. This one we've got three R groups pushing in to this carbocation. So this is the most stable out of the lot of them. Okay, so reacting hydrogen halides with unsymmetrical alkenes, this produces two different products, okay, as you can see here. So this is prop-1ene, and again we're going to use the same reaction obviously with HBr. So obviously this is going to react, same mechanism as before, and we're going to form this primary carbocation. Remember, this is less stable, and so this is the least stable one, should I say, and this is obviously going to be formed less often. Now, as opposed to going the other way, so this time if the hydrogen now adds on to the end here instead, as you can see, instead of on the middle, we form a secondary carbocation. And this is formed a lot more often because it's a lot more stable. So the mechanism for the top one is 1-bromopropane. This is a minor product. And this one is going to form a much major product, which is 2-bromopropane. So 2-bromopropane is going to be more likely to be formed with this unsymmetrical alkene compared to the 1-bromopropane, which is your minor product. Now, we do have this special rule. We call this Markovnikov's rule. And basically, this is the his rule, basically saying the major product, when we add hydrogen halide to an unsymmetrical alkene, is where the hydrogen adds to the carbon with the most number of hydrogens attached already. Now, you can see here, here's the hydrogen here. Now, this hydrogen is going to attach to either a carbon with one hydrogen or a carbon with two hydrogens, because this has got the most number of hydrogens attached to it. If the hydrogen attaches there, we form the secondary carbocation, is then more stable. So this is basically what Markovnikov's rule is talking about. Okay, so let's have a look. Remember we talked about alkenes and polymers. So alkenes are monomers, and they join to form addition polymers. So polymers are made from monomer units, and they can be natural, for example, proteins and natural rubber, or synthetic. So, for example, polyethylene, sorry, not an N, and polypropylene. So polymers have been used for a while. So in 1844, this person called Charles Goodyear discovered vulcanized rubber, and he added chemicals to natural rubber and made it harder wearing rubber suitable for tires. Obviously, we still see Goodyear tires today. They're quite a global brand, but it was discovered somewhat by accident by Charles Goodyear. I mean, he actually discovered vulcanized rubber. So in the last 100 years, the polymers obviously developed. Now we're forming polyethylene. Should be an ene in the end. Again, my autocorrect has obviously taken over. Polyethylene, nylon and Teflon, for example, and these polymers obviously revolutionized the way we live now. Obviously, you see plastics everywhere now, to be honest, so they really have revolutionized the way we work. And obviously, new polymers are being synthesized all the time. Smartphone watches, smartphones, and digital technology is revolutionized the way we use plastics nowadays. Okay, so to make polypropylene, we need a monomer of propene, and we need to add a few of these together to make polypropylene. Okay, so here, this is the monomer of propene, and the double bond opens and it forms the polymer. There it is there. Okay, few things to notice. N means we've got lots of repeat units of this. Obviously this is one repeat unit, but you can see that the double bond is no longer there now, and we have these trailing bonds, which are these things here. So these extend beyond the brackets that we've drawn. Okay, and this is basically showing repeat units of 2. So this is 2 repeat units. So we take this and we repeat it twice. And this is 2 repeat units, this is 2 monomer units. Notice, because we're showing a very specific amount of repeat units, we don't put the N at the bottom. So polyalkenes, these are saturated molecules, normally non-polar, and hence they're unreactive. So they don't degrade well in landfill either. So they're not great plastics, to be honest, in terms of sustainability. Okay, so let's have a look at how we can dispose of these things. Most polymers are not biodegradable, so they need to be disposed of carefully. So landfill is pretty much useful for plastics that are really difficult to recycle. Not all plastics can be recycled, remember. Either too difficult to separate as well from other materials, so you might see certain food products with all sorts of things on, like foil lids, cardboard surrounds, plastic lids, etc. So really difficult to separate them. And there's not enough plastic to extract it to make it economically viable, so it's only a tiny bit. It normally just goes into landfill. It's not very sustainable though. Loads of land's needed. It's becoming really expensive with the landfill tax, particularly in the United Kingdom, where we have a landfill tax. It costs a lot of money just to put it into landfill. And also there's a need to obviously reduce our reliance on landfill as well. Maybe we should be a little bit more resourceful with what we've got. We can obviously recycle them, and most plastics are recycled. So most plastics are made from crude oil. It's a non-renewable source, so we can't get it back. So recycling means that we don't have a heavy reliance on crude oil for making the plastic. So some plastics like polypropylene, these can be remolded into new objects, which is pretty good. And other plastics can be cracked. So this is basically the polymer chain is a long polymer chain in this plastic, broken down into shorter ones, and we can use that as organic feedstock. This is basically just more raw material which can then be used to make completely new substances. Incineration, so this is burning. So this could be used if the plastic can't be recycled again. And when we burn the plastic, we can also generate electricity, which is again a little bit more sustainable. However though, when you burn certain plastics, and vast majority of them, they release these toxic fumes. So you've got to monitor it really carefully, and you've got to control the emissions that's coming out of these places. In particular, things like PVC produces HCl, which is particularly harmful. So we don't want to be burning too much of that, really. And we can use, though, to try and reduce the harmful emissions, flue gas scrubbers, and these basically neutralise the acidic gases produced when we burn PVC. And obviously, we can just fire this base like a slurry at the acidic gases, and we form a neutral compound. Okay, so when we're making polymers, scientists need to think of specific things when we're making it sustainable. So reactants, using reactants that are environmentally friendly and not dangerous, that's quite important. Solvents, we're looking at little and low hazard solvents like water. Raw materials, so we're using raw materials that are renewable. Energy, the energy use should be as low as possible. Catalysts can be used to reduce the energy consumption. Waste, when trying to reduce the waste products, especially for toxic and environmentally harmful waste products as well. And longevity, make the product out of sustainable plastic, or plastic that is suitable for its use. And if the products last longer, then we don't need to manufacture as many of them. Which is going to be much more sustainable in terms of plastics. Okay, we can get plastics that are biodegradable. These decompose naturally. So biodegradable polymers, these decompose under certain conditions by organisms. These biodegradable polymers are made from both oil fractions and renewable sources. So for example, starch. They're more expensive than non-biodegradable plastics, but still they are a little bit more environmentally friendly, so to speak, than your non-biodegradable ones. So for biodegradable plastics to degrade, you need a really good supply of oxygen and moisture, and you can see this is like basically it's like a compost heap, but compost works in the same way. Composting, you have loads of oxygen that can be supplied around it, and it's quite warm as well, loads of water in there. And we can use biodegradable plastics in frost protective sheets, which is pretty useful. Basically, we put them over the plants. They're made from polyethylene. Again, that's supposed to say ene in the middle there. And starch grains. So over time, these microorganisms break down the polymer, meaning that you don't need to dispose of the old sheeting. So it's pretty useful, especially in farming. You have to, if you've got huge fields with loads and loads of crop, you don't want to be then going back out again to rein in the plastic sheeting. If it biodegrades and decomposes, well, surely that's going to be a better thing than trying to go back out and collect it in. It's much more efficient for the farmer. So the advantage, crude oil doesn't need to be used, which is non-renewable. Another advantage is its plant-based polymers degrade and they release carbon dioxide. And this carbon dioxide is absorbed by the plants to make the polymer in the first place. So for example, starch can be made from potato plants, etc. So pretty useful for that. Another advantage is that actually over the product's lifetime, plant-based polymers use less energy to make than oil-based ones. So we're being more resourceful with our energy supplies or the resources that we've got available to us, and so therefore it's more beneficial to use plant-based ones than oil-based ones. Okay, and that's it. That's the end of part 1 of topic 6. It's a very big topic. I appreciate that. Like I say, these slides are available to purchase. If you just click on the link below in the description box, you can get a hold of them there. Please support this channel by subscribing. The channel really is only as good as it's the people who support it. So your support is much appreciated. So if you just click on the little circle in the middle there, and you'll be able to subscribe direct to the channel, and you'll be able to get all the latest updates to the videos that are uploaded as well. But that's it. Bye bye.